Hello, today I'm going to explain deletion in binary search tree. So deleting a node in binary search tree and ensuring that the tree should remain balanced after deleting that node, we need to follow some scenarios here. So let's see what are the scenarios here. So the first scenario is for the tree with no children, means the leaf node. Leaf node means no children. Leaf node means the node with no children. So here we can see there is a tree with no children, so we'll simply there is this node. The second scenario is for the tree which has only one child. So here we can see there is a tree with only one child at the left and there is another tree with only one child at the right. So it simply replace this child to the root. Third scenario, the third scenario is for the tree with two nodes. So here we can see there is a tree. Suppose if we want to delete a node with a key value 15, so there is two nodes. Here we can see at their left there is a node and at their right also there is a node. So to delete a node 15 here, the binary search tree provides us a technique in form which is called in order successor. So what in order successor gives us, the in order successor gives us the smallest key in the right subtree. So the in-order successor gives us the smallest tree in the right subtree. What I meant by this is, like suppose if you want to delete this 15, so we'll go to its right subtree and find its smallest key there. So as we can see here, the smallest key in its right subtree is 18. The smallest key is this 18. So we'll simply put this 18 to the node which we want to delete. And after that, we need to delete this node also in the right subtree. Now let's move on to the code part to see how we can implement this. So let's implement the deletion in BST. So for that, first we'll need to create the BST node here. So BST node, then we'll have our constructor function which will have a key and will provide the context to it. This dot key equals to key, and we'll also have this dot left which will point to null at the start, and also this dot right which will point to null at the start. And this way our node is created. Now we'll create our bst tree which will have a constructor function which will have this dot root pointing to null. And now our bst tree is also created. Now we'll implement our deletion function here. So suppose we will do delete and we'll get the key that should be deleted. And now what we'll do, we'll assume that we are replacing our root we are replacing our root that should be deleted by the given key. So by saying that we are deleting this, we are replacing this root, it doesn't mean that this is the root which is at the top of the tree. It may depend, like for example, we will assume that wherever whichever key is given to us, suppose it's given 9 to us, so this will be our root. uh, this will be our root for 19, this will be our root. So it doesn't necessarily mean that whenever we will perform certain operation on this dot root, it will only affect the root of the top of the tree. When we are recursively traversing for our key, it will make that key only the root. So anything performed on that root will returned as a result to us. So here this dot root will be replaced by a, we are taking a helper function here, delete node, which will have a this dot root along with the key. Now this the delete node will have the majority of the logic handling in there. So now let's create this delete node. We'll take node comma key. Here node is just for the naming. It's the node always points to the node is always pointing to the this dot root. So the node is always pointing to this dot root. Now we have to check if node contains if there is a node present or not. So we'll check for the node. We'll check for the node here. So we'll perform if node is equals to null. We'll simply return null. We'll simply return null. Now what we'll do is we'll traverse for our key. So suppose here, like there is a 4 here, there's a key 4 given to us. Now we have to traverse for this key. So we'll check if our key is less than this node dot key, we'll traverse here, and vice versa. If it's greater than the node dot key, we'll traverse to the right side of the key. So like how we can perform here is like else if our key is less than node dot key. If our the given key is less than the node dot key, then we need to traverse in the left direction. So node dot left will be equal to this dot node, and we'll change the reference here. Now the node given to the delete node will be node dot left comma key, like keep on traversing till it finds the key value there. Same will do with the right part of it, like else if key is greater than node dot key, then node dot write will have this dot delete node node dot write comma key. So after these two condition, we have ensured that after this, in else case, we know that we have got the key. Like we know what we have got the key. Now what we have to do is we will have to follow the scenarios that we have discussed here. Like now we have to search now to see if the given key is a leaf node, or it has a one child, or it has a two nodes here. So let's see here. So let else. Now here first we'll check for leaf node. So what we'll do is if node dot right is node dot left is equals to null, and node dot right is equals to null, it means it is a leaf node, and will simply return null. Will simply return null to them. And after that, if this condition is not followed, means we have to move to the another condition, which is if it contains one child. For one child, what we can check is if else if node dot left is equals to null. If node dot left is equals to null, we'll simply return the node dot right to it, because it is its only child. So we'll simply replace that to the node dot right. So we'll simply do return node dot right. After that, in an else if condition, if node dot right is equals to null, we'll simply retain the node dot left to it. So now we have to check for a condition where it has, you can say, two nodes. So for two nodes, as we have discussed, we'll make use of in order traversal. We'll make use of the in order successor. In order successor. As we can see here, we are making use of in order successor. What happens in order successor is the in order successor will give us the smallest key in the right subtree. So we'll make use of an helper function here, which will give us the smallest key. So we'll store it, let's suppose in a temp node. So the temp node equals to find find min node, and we'll probably give him the node dot right, like the right subtree, and give it to me the value. Now we'll got the temp node. Now we'll simply replace node dot key equals to temp node, and now that node dot right part needs to be resetted, because as we can see here, like if this 18 is replaced here, so this 18 needs to be get deleted. So we'll again perform this dot delete node, and we'll pass on here node dot right and the temp node here. So now we'll make a then after that we'll simply return our node here, so that this dot root, and now we'll create a small helper function here, find min node, which will have the node here, and we'll simply need to check while this node dot left not equals to null. Simply, if it's not null, simply move ahead to its left, traverse till we get the smallest key value, and simply return the node here. We'll simply return the node here, and this is the code for the deletion in BST. So now we have checked if it's first of all we have checked if it's a null or not. Then we have traversed in the left or right to search whether our key is there. If we got the key, we have checked the scenarios here for the leaf node. If there is one child, or for the two nodes, we have followed in order successor technique, where we have stored a temp, where we have a temp node which stores the find min node value, and then we will replace that temp node with a node dot key, and we'll make sure that the node dot write will will get changed after that, because we have to delete that node that has replaced the root. And this is the find min node helper function, which will give us the smallest key in the right subtree. Thank you.